Glad to see everyone. My name is Alex. I am a compiler front-end lead at solx. The compiler was originally created by Matter Labs, but now a part of it has been moved to a Nomic Foundation. And today I will be talking about solx mostly from the perspective of our interaction with the solc compiler. And I will show a couple of problems we faced and how we fixed them, and how reusable components such as LLVM framework helped us in our journey. So the story begins in early 2021 when Matter Labs was building zk-sync VM, a virtual machine with a custom instruction set, which was register-based. And we were a small team of one front-end engineer, one LLVM engineer, and a QA who had to deliver a compiler for this virtual machine in roughly 1 year. The time frame was challenging, so at first we had no idea if we could do that, but we started to look around for the reusable components we could reuse and deliver faster. At first, we looked at the solc compiler because it was the only compiler available back then. We looked if we could reuse it in a sense that it would emit a different bytecode, like a zk-sync VM bytecode. But unfortunately, its design was quite EVM-centric and tailored towards emitting EVM bytecode. But however, it had two pipelines, EVM assembly and YUL, that could emit IRs that could be consumed via different tools that are calling solc via CLI. EVM assembly was quite low level, stack-based, and really close to EVM bytecode. So we looked at YUL first. It was just added a couple of versions ago, really early stage, not battle tested, but it was nice and simple and easy to work with. So we wrote a small adapter between YUL and the LLVM IR. It's the red area on the left. It's basically taking YUL and translating it to LLVM IR that can be later compiled to the zk-sync VM bytecode. And for the middle end and back end, we used LLVM. The choice was obvious because it's kind of the biggest and the most mature compiler framework in the world. We could get the decent performance from the LLVM middle end, and LLVM backend also allowed us to reuse all the infrastructure in LLVM and deliver the backend many, many times faster, probably around 10, 20 times faster, depending on how much of the infrastructure of LLVM we want to use. Like if you want to repeat the same quality, the same number of features as an LLVM, you will likely spend decades of engineering time. So this is how our pipeline looks like. We reused all the green area, and we only wrote ourselves the red areas, which are zk-solc adapter between YUL and LLVM IR and the zk-sync VM backend itself. So in total, we reused more than 95% of the code base, and we successfully delivered the compiler in 1 year. Users could deploy Solidity contracts to zk-sync VM, and since we have ported YUL to LLVM IR, it was now possible to use all the other backends available in LLVM, and this is what happened 3 years later when guys from Parity forked zk-solc and changed just a few % of the code base and compiled YUL to RISC-V. So it is now basically possible to compile Solidity to RISC-V using their work available at the link, at the GitHub link below. Some aspects of the developer experience were not great. For instance, YUL was only available in Solidity 0.8, and it had semantic differences with L1 because solc is using the EVM assembly codegen by default, so all our contracts had a couple of differences with the contracts on L1. It also suffered from compiler crashes and long compilation times. So at some point, we realized that we had to support the EVM assembly as well. It was challenging for a couple of reasons. And the reasons were that EVM assembly is a very low-level stack-based representation, and LLVM-IR is register-based. The second reason is that the control flow is not explicit in EVM assembly. So if you see these jumps, you don't really know where the jump is going to. You basically have to rebuild the stack first, and then after rebuilding all the stack states for each instruction, you can have an idea where the block is going to. So we had to translate the representation on the left to the representation on the right. For this purpose, we created this IR to fix these both problems. It is basically rebuilding the stack and maps all the stack slots onto virtual registers of LLVM-IR. And it also solves the problem of the control flow. You can see the predecessors next to each block. So basically, we are tracking all the jumps and mapping the destination tags onto these jumps. We had a lot more challenges than this, but I will not go into them low level in this talk. Probably deserves another one. I'll just say that it didn't come for free. We had a couple of performance regressions. We had to deliver a couple of extra optimizations. And we had to fork solc to get rid of dynamic jumps. Basically, we did that in all versions of Solidity. We had to maintain 80 Solidity versions for 3.5 years since we released the first EVM assembly support. And the translation itself was complex, and the algorithm was kind of fragile. However, we finally supported all Solidity versions on the ZK Sync VM, and they all could now be compiled to other targets in LLVM, just like Yule before. Of course, we didn't want this to become a one-time job, so at some point in mid-2023, we had grown to a team of 5 engineers, and we realized that we could reuse all this expertise and the code bases to deliver a greater public good for Ethereum, an alternative compiler for the EVM. So we asked one engineer to start working on an EVM backend inside LLVM. And we knew that some people tried to do this before. A couple of other projects tried to deliver LLVM framework capabilities to Solidity, but they were abandoned for a couple of reasons. And after this, the dominating idea in the Ethereum community was that LLVM was not suitable for the EVM. However, it did not make a lot of sense to us because we knew that there was already one target in LLVM implementing a stack machine. It was WebAssembly. So we based our stackification algorithm on WebAssembly backend, and a few ideas we also borrowed from the solc backend. So here we are basically doing the opposite of what we had to do with EVM assembly. We are turning registers into stack slots. So in 1.5 years, we had a working backend. It was passing all the tests for Solidity from the upstream repo, and also some tests that we had written for ZK Sync VM. However, nobody could use it yet because we had no front end. Or to be more accurate, we had 90% of the front end hidden inside ZK solc. On the first infographics, you can see that the target-independent nature of LLVM-IR allows you to have your front end as generic as possible, and you can basically reuse 90% of the LLVM area lowering from ZK Sync VM to EVM to RISC-V and all the other targets. And that's what we wanted to do. We just forked ZK solc, and we got solx frontend out of that code base. We still reused all the middle end, all the LLVM code you can see on the second chart. It's like 800,000 lines of code. And anyone can do that with our code base, since we are almost 100% MIT Apache licensed. GPL version 3 is only for the parts where we interact with the solc, like the bindings between C++ and Rust code. So yeah, we had solx, but we did not want to release it just anyhow. We wanted to deliver something special to the community and make users love solx. So we came across this Solidity survey that had been listing the same top 1 problem year after year after year. It was stack too deep. And we realized that with all the power of LLVM, of all the layers of abstractions it provides, it was not such a big deal to fix. So here is what we tried. On the left, we are basically running the stackification algorithm once and recording how many variables did not fit into the stack, and then we rerun the compilation with all these variables moved to the heap. And since our solution works on the backend level, it solves stack too deep for all code gens and all pipelines and all Solidity versions with 100% accuracy. If you still have stack too deep with the solx, it's a critical bug, please submit it to us. It's a P0, we will fix it. Yeah, on the other side, you can see that Yule, even in the latest version, still has these crazy errors. So apparently, the solution is not perfect. Yeah, here's what we are doing. It's basically the same as the previous presenters talked about. We are allocating the spill region on the heap. We are moving the memory guard further, and the user memory shift further, and all these variables from the stack, they're allocated on the spill area. So yeah, stack too deep solved. Any code gen, all pipelines. And we have delivered the first LLVM-based compiler for Solidity. We saw some moderate gas usage reductions from the default LLVM optimizations from the middle end. But unfortunately, like any first release, we suffered from long compilation times and bytecode size issues, and that's what we had to solve in the next versions. We decided to fix the compilation time first because we knew that it was a really hard problem for Solidity developers, especially with the Yule, with the via IR pipeline. It didn't take us a lot of time. We only spent like 1 month on this. And in the beginning, solx was 3 times slower on average. It kind of depends on what pipeline you're using. EVM assembly is really fast, but we knew that via IR is going to be made the default pipeline, so we paid more attention to that one. And we wrote a small tool that would benchmark all the parts of the pipeline, break it down by contracts, by translation units, and so on. And we found out these 2 problems were the biggest black holes in the compilation time. solc is completely single-threaded, so if you have 64-core machine, only 1 thread is used. So basically, you are having solc that is 64 times slower than it should be. And the second problem is that we still had both optimizers enabled. We did not want to turn off the Yule optimizer because perhaps we'll have gas regressions. We just wanted to keep them both. So we tried to add multi-threading to solc, but the coupling between components was so high and there were so many global variables, the whole design was not suitable for multi-threading, so we only turned off the solc optimizer for Yule, and here is what happened. This is not an average case, this is an extreme case. I just want to showcase it because Aave v3, it was kind of very infamous for having very slow compilation times on Yule. After turning off the Yule optimizer, the compilation time reduced by 8-fold, and the middle end and back end stage itself, it was 30x faster with the LLVM pipeline rather than Yule pipeline. And it's not the end of the story. After we turned off the Yule optimizer, solc was still accounted for 75% of the total running time. This is the dark blue stripe below. And the reason is mostly because it's single-threaded. Like Aave has around 100 contracts, or maybe 400, I don't remember. If you scale the front end and run it in multi-threaded mode, you can probably reduce these 80 seconds by 12 times, and your front end will be just executed in 5 seconds. So yeah, an average compile time reduction was like 3-4x compared to solc. And the last problem, the bytecode size. We could not deploy a lot of projects because they just used to exceed the EVM bytecode size limit. The bytecode was 6% larger on median, but some contracts were 50% larger. So we investigated what was going on, and we still had those chunks of zeros and Fs in our bytecode. We had to get rid of them. So we implemented this constant unfolding algorithm that would just unfold these big constants that were usually representing negative numbers, such as -1, into something concise, but probably costing more gas than just simple push. We also implemented an adaptive algorithm that would track the EVM size limit, and when the bytecode is close to the EVM size limit, it would unfold more constants or just apply additional optimizations, and this is all well tuned. We are exposing some variables parameters that can help you to tune the pipeline in case you need more gas optimizations or more size optimizations, and still LLVM will make sure that you are not exceeding the bytecode size limit. So this is the bytecode size benchmarks. We are roughly 50-50 on par with Yule because we are still preferring gas to bytecode size, but on median, we are 11% smaller than the Yule pipeline and 28% smaller than the EVM assembly pipeline. The gas benchmarks, we have been working on the gas optimizations since the very first release, so there is no specific release focusing on them, but on the last release, you will have a roughly 13% reduction of the gas in any pipeline. They're kind of similar in the results, but you will have the reduction on almost all contracts, like 90-95% of contracts are cheaper in solx than in solc. The most important topic, I guess, how about testing and security? So on the left, you can see all the tests and projects we are running on every patch and every commit. 24 Foundry projects, basically all of them that could be integrated in CI. It's kind of a few dozens of thousands of tests. And we are running all the upstream solidity tests. We are running zk-sync VM tests that we had written before, and LLVM unit tests, of course. We are also being fuzzed by an external team. The fuzzer is being run on solx 24/7. It already found some compiler crashes. And speaking of where we are security-wise in comparison to solc, the data shows that we had the same number of found issues in solc and solx. So there is no strong reason to believe that solx is less secure at the moment than solc. We are also aiming to have more than 90% test coverage for the front end and the back end. We want to integrate the contract sanctuary, and we are open to discussions about front end audit and back end audit. We have very little expertise here, but I hope that the community will help us to make solx more trustworthy and make users not afraid of it. So when solx, we are currently recommending using solx for development. That is, you can just compile your project with solx while you're developing it, but then deploy it with solc. Or if you really suffer from stack-to-deep issues, you can just switch to solx for non-mission critical projects or projects where you have 100% test coverage and where you're really confident. And of course, when you have done that, please share your experience with us in our Telegram channel or in Twitter. On the left, you can see all our resources where you can reach out to us. And please try solx today. Do we have time for Q&A?
Awesome. Thank you so much. 2 questions for you, Alex. How relevant were existing LLVM optimizations were to the EVM?
Could you repeat the question?
How relevant were existing LLVM optimizations were to the EVM?
So we can answer this question by looking at what we had in the first release when we barely started working on EVM-specific optimizations. We had some moderate guess improvements. I think we were around 3 to 5% more efficient than solc. So basically, it gives us the idea that the middle-end optimizations from the LLVM, the default ones, they were enough to be roughly viable for an EVM pipeline. So you could deploy the contracts, and you could roughly have a decent gas price for your methods. Most of them were relevant because they are relevant for all targets. They are very target independent. It's just something basic like that store elimination, like loophole optimizations, and so on.
Are there any plans for Foundry to support solx?
For?
Foundry to support solx?
I think Foundry is generic enough. It can just use solx already with a different profile, so you can just declare a new profile and specify the path to your solx, but you still have to download the executable locally and specify the full path. I don't know about Foundry supporting solx as the first-class citizen because we still have no either scan support, and our release pipeline is not stable yet. So maybe we will change the versioning, maybe we will change this or that, but overall, you can just use solx locally with Foundry and Hardhat.
OK. And one question is, what are the differences between solx and Solar, the new paradigm Solidity compiler?
Well, as far as I know, Solar is targeting different backends, at least 3 or 4 of them, but we are targeting only one backend, so we are putting all the effort into the LLVM pipeline. That probably will make us more efficient with this one single pipeline.
Awesome. Another fun part is that there's a Solar talk as well, and that's going to be the last talk of the day. So please make sure that you wait until the last talk of the day and then catch all of our speakers to pick their brains about their projects. But thank you so much, Alex. That was a wonderful talk. That will be it.